Hi, I'm Rosamaria Carraro, a PhD student at Universidad de Valparaiso, working with Patricia Arevalo. And today I'm going to show you some preliminary results of a work with Francesco Scianca on the origin of the relation between the X-ray luminosity and the galaxy's stellar mass using semi-empirical models. Many works have found that the evolution of the black hole accretion through cosmic time, which is often traced by the X-ray luminosity, follows a similar evolutionary track as a star formation rate. Here I'm showing some results from a work we published earlier this year with data from the Cosmos survey. And we are showing average star formation rate and black hole accretion rate as a function of stellar mass. It is not clear whether what we see arises from their common dependence on stellar mass or there is some sort of causality. This is what we decided to explore with a semi-empirical model. Our semi-empirical model allows us to generate a catalog of galaxies so that we can perform statistical study that can be compared with our observational results. We start by generating dark matter halos with a halo mass function. Then through abundance matching, we assign a central galaxy to each halo. Then to each galaxy, we assign a supermassive black hole through a scaling relation between the stellar mass and the black hole mass. Then, through an Eddington ratio distribution and a bolometric correction, we determine an X-ray luminosity in the 210 keV band. Finally, with a duty cycle, we determine which black holes are active and which ones aren't. We also assign a star formation rate using a new fit of the main sequence of the data from our previous work, so that more massive galaxies are more actively star forming. Just like we did with the observational data, we divide our simulated sample into mass bins and perform a bootstrap to derive more reliable averages of the observables. We are going to explore in this work a range of scaling relations, Eddington ratio distributions, and duty cycles, but we will see the scaling relation and the Eddington ratio distributions are the ones ruling the X-ray luminosity, not the duty cycle. Now let's see our results. Here we have the average X-ray luminosity against the average star formation rate of our simulated galaxy samples, and we also show our observational results. The data points are color-coded by stellar mass, and we simulated galaxy catalogs for different scaling relations from the literature. We can see that all the scaling relations generate an LX to SFR relation, in which more massive galaxies are more star-forming and more actively accreting the black hole. Each scaling relation produces a different relation, so this tells us that the scaling relation probably plays a role in determining the X-ray luminosity. So we went on to explore this. Now we will see a few plots with the LX X-ray luminosity to stellar mass relations obtained at redshift 1 by varying one of the model's relations at a time, and we compare the results from our model to observational data. Here we vary the scaling relation. It's a toy model in which we extend the Davis relation to lower masses. And we vary its slope from about 3 of the original relation, shown in orange data points, down to 1 with brown data points. This shows that the slope of the scaling relation directly affects the slope of the LX to M star relation, and our data is compatible with the shallow slope of the scaling relation. This is the same as the previous plot, but this time we assume the Gaussian Eddington ratio distribution in log lambda. And we can see that by decreasing the mean of the Eddington ratio distribution, we will only decrease the normalization of the LX to M star relation, with no effect on the slope. We see that our data is compatible with a mean Eddington ratio that is mass dependent and increases at lower masses. This time we vary the duty cycle, and in all cases we obtain the same relation, so we can conclude that the duty cycle does not affect the LX to M star relation. And as anticipated, the shape of the LX to M star relation is given by a combination of scaling relation and Eddington ratio distribution. As a last result, we now want to reproduce the LX to M star relation of our data with a Reines involuntary relation, which has the closest slope to our data. And we explore a range of Gaussian Eddington ratio distributions. The simulated samples that best reproduce the data have a mean Eddington ratio that goes from 10 to the minus 1 at redshift 2.7 and decrease to 10 to the minus 2.5 at redshift of 0.5. We see that we need a lower characteristic Eddington ratio at low redshifts, and it might be lower than previously thought. I will leave you now with my conclusion slides. Thank you very much for watching.